Good morning, everyone.
Morning.
Do you guys get enough sleep?
Okay, I think we should start now. So, is that clear, everyone?
Yeah, it looks good to me.
Okay. So first thing first. Well, to logistic stuff. First, about this week and next week, our schedule will be slightly changed because next week will be our last week, and we have to postpone our final exam to from Thursday to Friday. So what I decided is, this week and maybe on Monday next week, what we are going to do is we will introduce first the group action. Okay, and second thing is about this group action or this group representation theorem, and also the Silo theorem or Silo group. This is what we are going to do, and we hopefully will finish it on Monday. Okay. Well, I mean Thursday. Well, Tuesday next week, and then on the Thursday, which is our last class, what we are going to do is we are going to do some review. And if we haven't finished anything, we'll try to finish it. And I will also try to tell you my understanding about how to play with this second order magic cube. Okay, I will try to let you know how to play with it, and or some other stuff, some other easier stuff, so that it will be easier for you to relax and prepare for your final on Thursday night. Okay. So what we are going to test for your final would be everything until Silo group theory and application. Okay, which is I think in our textbook is section 7.5 something, I think, with maybe a little bit about the Bernstein theorem on 7.3, and also the group action, which is on 7.1. So basically what we are going to discuss would be 7.1 and 7.5 with a little bit on 7.3 of our textbook. Okay. Other than that, what we are going to discuss would be, everything not will be on the exam. Okay. And also well, since we've talked about a lot about the group theory on this last 4 weeks, so the final will highly rely on the group theory, not the ring theory. Okay, so there might be like 20% on ring theorem, on ring theory, and 80% on group theory. Okay. So that's for final. And also the homeworks this week would be the last homework. But then the problem is, when should you submit it? Okay. So the way I'm going to do is, for the homeworks this week, which is homework 7, well, homework 6, will be optional. It will be optional means, well, you can finish it, and then this homework will substitute one of your lowest homework scores, okay, if you finish it. And I can accept it, and then I will not count it, but I will use it to replace the lowest homework score in your history, okay?
What if we get homework 6 actually lower than our other homework?
Then it will not, okay? It will not be replaced anything, okay? It will be, if you want, it can be replaced. It can be used to replace the lowest scores among homework 1 to 5, okay? And it will be due on Tuesday. Tuesday, 7 p.m. So that I can finish grading on Wednesday and then give it back to you, and so that you may have some time to ask me questions about it. Okay? But again, this would be optional. Although this part of content is not optional in a final exam, but this time the homework is optional. Okay? It's up to you. You don't really need to rush to finish it. You could, but if you don't want, you can just take it optional. Okay. Well, sorry about that, because this semester is really, chaos or chaotic in some sense. So this is what I'm going to do for the final and for the last homework. Any question? Any question about your final, your last homework, or whatever?
So we will still get like 1 bonus point if we submit the homework.
That's a very good point. So the thing is, well, if you finish this homework, well, by typing in the text, then if you do not have like 5 points as bonus point by doing this typing in the text, then, well, you can get 1 more point. Otherwise, if you already get 5 points from typing the text of your homework, then, well, this homework will not count. Okay?
Okay, got it. Thank you.
So the maximum bonus point from typing the text you can get is 5 points. Okay? I just want to, well, give you more time on preparing your exam, because I believe next week you will have some exam more than this one, right? At least I know that for the ODE course, you will have the presentation and exam, right? Any other question? Any other question?
Can we just ask to make it like Tuesday later, just a bit later?
Well, what do you mean later?
Like, I don't know, Tuesday 12 p.m.
Well, what's the difference? I mean,
well, that's a lot of difference. I would say.
I think you will have your final for ODE course on Wednesday or Tuesday. I forgot, but whatever. I think you will have the the final on Tuesday, on Wednesday, and presentation on Wednesday, whatever, right?
Wait, do we have a final on Wednesday? Oh no, we're
I think you
screwed.
have the presentation on Wednesday for ODE course, right? So well, I think it doesn't change if I make it slightly later. It doesn't really change. I would recommend you, if you would like to finish this this optional homework, try to finish it by well, on the weekend, okay, so that you will have more time on. Well, unfortunately, in this course, we are not going to finish the final score. But well, I try to think about this, but you know, our university is slightly different from others. We have very rigorous well, skills or very rigorous schedules. Well, the scheme on the grading. So it's not appropriate for me to reschedule. Well, to curve everything, to curve this final scores for GPA. But well, I'll keep an eye. If I do find well, your final, which I'm going to make it slightly harder than your midterm. If I do see that your final scores is over too low, I mean, all of you are over too low, then, well, if everybody are very high, then I'll not do anything. But if everybody are over too low for your overall scores, then I'm going to curve your final, okay? And then so that your overall scores for GPA will not be so low, okay? But if I think everybody are doing well and this distribution of your final exam is okay, then I'm not going to do that. Even if, well, most of you do not get higher than 80, this kind of situation. Just for example, if nobody can get higher than 80, which I don't believe, then I'm going to curve the final exam scores, okay? But for your overall scores, I will not be able to curve it, okay? This is not something we are going to do. Sorry about that.
Sorry, I think we will have our ODE final on Thursday from 3 to 7. And like last time for the midterm, we got half an hour extended, which means that the ODE exam ends at 7:30.
Okay.
Yeah.
Whatever. If you do want, I can make it, well, change from Thursday 7 p.m. to Thursday 8 p.m. Okay, that's fine for me. Yeah, I can extend it for an additional 1 hour because well, for our exam you have 24 hours, so it doesn't matter if you have 25 hours instead. That's fine. But well, okay. Since ODE, well, the ODE exam will be until 7 or 7:30, then I will also postpone it. I will also try to make it from 7 p.m. Thursday to 8 p.m. Friday. Okay, that fair?
Okay, thank you.
But I don't think it matters. I mean, don't try to put everything in last minute. Okay, this will be really bad.
I just thought that maybe you can like postpone it until 8 p.m. I don't know. I don't know.
8 p.m. is fine. 8 p.m. is fine. But don't count on that. Okay, because we'll put everything until last minute. It's a very bad behavior, and sometimes it will really hurt you. Okay, this is not really good. Try to finish it as well. Sometimes like a Friday morning or something. Then I think that will be something that makes sense to me. Don't try to do it until last minute. Okay. Any other question? And again, the final will be slightly harder than your midterms, but not too much. Okay. Because well, I just think that your midterm is it's a bit too easy. Some problems are a bit too easy for you guys, and you guys are all doing very well. So I will try to make it slightly harder. Okay, for your fine. Will not be too hard. It will still be comparable to your homework. Okay, your homework will be the reference. Okay, so we will start now. Today, we are going to talk about, as we mentioned before, the group action, which is a very useful thing about group or in group theory, because this is a reason why we are interested in the group theory. The reason we are interested in group theory is we can use it to study some kind of symmetry of some object or of some set. And this, well, in order to do this, you will have to, well, know how to use a group acting on a set. Let me write the definition of the group action. The action of a group G on a set S is given by a homomorphism phi from G to the permutation group of S. What is a permutation group of S? It just means that you can try to exchange the element of S. And all this kind of change is kind of a permutation, right? And in most of the case, the permutation group of S could be seen as Sn, okay? Which is the permutation group of n letters. And this phi is, well, we denote this phi of G acting on S, where G is an element of this capital G, S is an element of this set S. We denote it as G dot S. But be careful here. This G dot S is not a group operation, it's not a group multiplication, right? It's one element on the group, well, acting on an element on the set S. But this set S, it may not have any structure, okay? It may just be some set. And that's for G belongs to G and S belongs to S. And be careful, this S may not be a group. So which means this is just a notation. And the phi of the identity is identity on the permutation group, which is, it doesn't change any element. It just maps S to S, okay? And E times S is S. Use our notation for any S in S. And also G, well, times G prime times S. G prime times S is an element in S, okay? And G times G prime times S is still an element in S. It's also equals to, by our notation, G, this multiplication is a group multiplication and acting on this element in the set S, okay? Here, because you try to map the group to the permutation group of a set. So this kind of homomorphism, it can also be seen or it can also be called as well, permutation representation of a group G. Okay, so of course this is kind of so-called a representation of a group G, because we call it a representation because you try to see G, which is an arbitrary abstract group, as some permutation. Okay, And by the way, so of course you have this kind of things to be the permutation representation. And there are some other kind of representation of a group. For instance, there is so-called the linear representation of a group. If, for instance, your set S is a subset of Rn or Cn or Fn, okay? Then you can try to find a homomorphism from this G to not to be the permutation set of S, permutation group of S, but to the general linear groups of Rn or Fn. Then this phi is so-called a linear representation of G. Okay, so which means you try to see G as a group of as a subgroup of general linear groups. Okay. So this is the group action. Of course, this is very abstract. So let me give you some example. For instance, we have the magic cube here. And as we mentioned before, playing a magic cube is more or less like you have a cube. And on each vertices, you have a number. For instance, here, this vertex, you have number 1, and here is number 2, and 3, and 4, right? And 6, 7, I'm sorry, 5, 6, 7, 8. So you have a group of vertices, right? 1, 2, 3, 4, 5, 6, 7, 8. And then you can try to use S8 to acting on this group S, which means, for instance, you can try to do some operations like this kind of operations, right? And this operations maps this vertex 1 to vertex 2, 2 to 3, 3 to 4, and 4 to 1, right? We rotate the upper level, this is counterclockwise, right? We rotate it. So let's say this is rotate the upper level counterclockwise, and this can acting on this. This is element of S8, and this can acting on S. Well, how does it acting on S? How does this element in this group acting on this set of points? Well, it can acting as below. This U1 maps to 2, U2 maps to 3, U3 maps to 4, U4 maps to 1. And U5 equals to 5, U6 equals to 6, U7 equals to 7, U8 equals to 8, right? So this is, you rotate the upper level, this upper surface by counterclockwise, okay? So this is how, and then all this kind of map, or all this kind of operations, like you rotate this upper surface, or the right side, or the left side, or the bottom, or element on S8. and they can acting on this S. Okay, so this forms this kind of operations can be seen as a subgroup of S8. Well, actually, it should be the whole group. Okay, but this kind of elementary operations can be seen as a subgroup of can forms at least a subgroup of S8. So which can acting on this set S, the vertices. Okay, and another example is well, of course you can use a group G. This one you use a group, maybe a subgroup, maybe the whole group, acting on the set of 8 letters or 8 numbers. Of course, you can also use a group G, acts on itself. Okay, then you can see that, okay, then that means, okay, every element in G, well, it is naturally defined G, this element can acting on this group, this whole group G, right? And G acting on A is equals to G times A. And G acting on B is equals to G times B. G is an element, A, B are both elements in G, then G can acting on, this little g can acting on any element on this group G. Okay, so this gives you a homomorphism from G to the permutation group of G. You try to see the element of G as letters, and then the permutation group is just you change all the letters of this G. Okay? Any question? Another example is, suppose you have a subset of G. Okay? Then this G, again, this G can act on, well, it can act on this set of cosets of H. Remember, this S, again, is just a set. It does not have any group structure because you only have this H is a subgroup of G. It's not a normal subgroup. So this S has no group structure. But you can still use G acting on this set, right? In a very natural way, which is, okay, this G, well, or maybe we write it as phi G will be a little bit better. Phi G acting on an element on G over H. An element on G over H is a coset of H. Don't forget this. It's not an element in G, it's a coset of H. Okay? It's equals to G times AH. Right? This is most natural way to define the group action on this coset. You're trying to do something like a permutation of your coset. Okay? Any question? And last example is where we can go back to our geometry example, which is this symmetric group of a square. This group can acting on this 1, 2, 3, 4, this square. Right? So basically, you can think it is the symmetric group acting on the set formed by, well, 4 letters, 1, 2, 3, 4. But it has some geometric structures like this. Okay, but you can still define what is an element on this group acting on this square, which is you try to do the rotation or the reflection. Okay, that clear? So, question?
Yes, so basically, we didn't define anywhere in the action that we cannot really say, for example, interchange like, I don't know, 1 and 4 and just leave 2 and 3. Like,
Well,
it's kind of like physically impossible, but like, can we define action to be like that?
well, you actually cannot, right? Because this group, well, this set, you see, this is a trick. The set here is actually does not allow you to, to change 1 and 2, right? So which is why what I'm saying is you're trying to use the element here to acting on this kind of things, okay? You can try to think it is more or less like, SQ can be seen as a subset of S4, right? But in real, this SQ is not a whole S4 because there are some elements on S4 which you cannot find on SQ. You cannot find the corresponding things on SQ. Okay, so which is why what we are thinking when we talk about the group action is you try to embedding your group to something you are familiar with, which is a permutation group. Okay, so that it is something easier for us to understand. And of course, if you do not have this kind of geometric object, if you only have the set 1, 2, 3, 4, then it is, you can use any subset or even the whole S4 acting on this set 1, 2, 3, 4. Okay, so that's different. For group action is something you try to make it more clear in the sense of the permutation group. You try to write the group as a subgroup of the permutation group or as a subgroup of the general linear groups. But that doesn't mean your original group is, is actually something on your GLNR or something on permutation group. Okay, this is you try to understand the group. You try to understand the group structure. Okay, if that is clear, then let's try to do something fancier. Okay, now what you have is, you have a group action. Okay, then what we can do is we can somehow, based on what we have, this group and S, we can somehow define something. For instance, that G act on a set S. Don't forget, it's always a set. Okay. Well, if we do not have any particular thing to say about S, it's just a set. And let okay, I will try to. So that you will not see any shadow, I hope. Okay, I guess, does that look better? Okay, anyway, if you cannot see it, let me know. Okay, let me know immediately. And let's say we have an element in S. We define the orbit of S, of this little s, is the orbit of S is S prime in S such that S prime is equals to GS for some G. Well, I hope you have seen this kind of obvious stuff on your ODE class. But if you haven't, then that's also normal. Well, but this kind of obvious stuff is also very important in ODE, in dynamical system. Okay, I'll give you an example to say what's the meaning of an orbit. And the stabilizer of S is GS, this kind of G in G, such that it doesn't change S, which is why we call it a stabilizer. Okay, GS is equals to S. Okay. So what do we mean by an orbit? An orbit is something like, well, you can try to imagine, well, let me see here. For instance, you have a point here, and the group action will try to move a point here to somewhere else on this group, okay, on this group. And then this orbit of this point, it just means you use all the elements to hit this point, and then it forms some kind of a track of this point, or an orbit of this point. For instance, again, let's go back to our magic cube. For instance, this you rotate. You try to rotate to the right side of your magic cube. It's R. Let's say actually you rotate it clockwise, so it's R prime or R inverse. Then, of course, this kind of operation forms a group. It can generate a group. Okay. Then we can consider this group acting on our magic cube, right? If we use this group to act on our magic cube, then let's see what happens. If we use it like that, then this is our to make life easier, let's still use this, well, counterclockwise rotation to be that, so that it will make life much easier, because our 1, 2, 3, 4, okay, 5, 6, 7, 8. Well, we can try to think about this, well, rotate counterclockwise of the top of the, well, upper side of your magic cube, and this operation, it can generate a group, right? This group has order 3, right? Well, has order 4, I'm sorry. This group has order 4 because you rotate it 4 times, then you go back to the original position. Then that means we can use it as a group to acting on this set, the set 1, 2, 3, 4, 5, 6, 7, 8. Then we can try to see what is the orbit of, for instance, point 1. Well, the orbit for point 1 would be, you can do nothing, right? The identity acting on this, well, point 1 is 1. Or you can use you can rotate it once. Okay, then this maps 1, let's say it maps 1 to 2. Or you can rotate it twice. then it can map 1 to 2 and then 2 to 3, right? And then you can rotate it again, then that means U cube maps 1 to 4. And you don't have any other operations on your group, right? So which means you only have 4 elements on your group, and all these elements acting on this point 1. So the orbit of point 1 under the action of this group should be 1, 2, 3, 4. Okay. Similarly, the orbit of point 2 is also 1, 2, 3, 4. The orbit of point 3 is 1, 2, 3, 4. And the orbit of point 4 is 1, 2, 3, 4. But you also know that the orbit of point 5, well, it doesn't change it at all, right? You rotate this upper side, it doesn't change anything for the downside, for the bottom side, right? So which means the bottom, well, the orbit of point 5 is always 5. The orbit of point 6 is 6. The orbit of point 7 is 7. The orbit of point 8 is 8. Okay, that clear? And then you can see that the stabilizer of point 1 is just an identity on this group. So does 2 and 3 and 4. But the stabilizer of 5, 6, 7, 8 are the whole group, right? And you can imagine, well, something must be true, and it's easy to prove that. Very easy proposition. GS is a subgroup of G. Okay. Any question before we move on? Any question? Okay. Then, well, what we can see is there are some kind of very special action. We have, well, right now I'm going to give a name of it. We call an action is transitively if there exists only one orbit. Okay, what does that mean? That means, okay, well, for instance, go back to our example. If we want some action or some group is transitively, then that means we want some group that can make, if you want to change this point or this cube to any cube, there at least exists one operation it can do that. It can change from this 2 to 1 or 2 to 3 or 2 to 4, 2 to 4, 2 to 5, 2 to 6, 2 to 7, 2 to 8. Both are possible. If for any cube you can do that, then this action is transitive. If for any point on S you can always do that, then we can say it's actually a transitive. It's a transitive action. Okay? And well, another thing is we call, well, maybe I will not call it an action. Let's call it the representation, because it's not only for the permutation, it's also for the, well, for the linear group. We call a representation faithfully if this homomorphism G from permutation group of S is an injection, or GS equals to S for any S implies G equals to 1. Okay? So we can see that, well, all of this kind of representation at this moment we have seen are faithfully. Almost all of them are faithfully. Is there anything that is not faithfully? Probably yes, right? There must be something, some representation, or some group action, which is not really faithfully. Which means there might be two elements on G. If you acting on a set S, then you cannot really see the difference for these two elements, right? Which is why we call this kind of representation it's not faithful. Oh, sure. What's the meaning of this transitively? Transitively simply means if you have a point on this set, then this group action can make this point anywhere on this set, anywhere you want. Okay? So which also means for any 2 points on this set, there is an element on this group such that this element can map this point to this point. Okay? This is the meaning of transitive, which means you can travel to anywhere you want by using this group. And faithfully means, okay, this group can really be seen as a subset of the permutation group of S, which means any two elements on this group are different under this representation. Okay.
Does it mean that like the the number of elements in G is less than that of permutation of S?
Well, not necessarily. For instance, the number, well, you cannot really say any relation between these two guys. For instance, you can try to think about this example. In some GL and F, well, for instance, F is only a finite field, for instance, Z2 or ZP. Then what you can do is you can try to see an element on this on this group acting on the set acts on the set, say acts on the set, say R, or maybe that's not a good example, but it can acting on the set well, whatever, on Z or ZP or F or whatever you want. And how does it acting on it? Well, the acting we can define to be, okay, phi from GL and F to the permutation group of Z or ZP to be phi of an element or a matrix of this set acting on an element on this Z, on Z, to be the determinant of this G times N. Okay, then you can see that this representation, this is F, I'm sorry, permutation group of F, this representation is not a faithful. It's not a faithful representation because on this embedding, you lose a lot of information, right? But you cannot really say, okay, well, there are some relation between these two, the element of these two sets. You can just say that you lose a lot of information, no more than that, under this representation. Okay, so this is just an example.
Yeah, by the way, I have a question.
Sure.
So the definition for transitivity says that there exists only one orbit. Does it mean that for every element in the set being acting on, like, say S, like for every element in S, the orbit is the same?
Yes, yes, that's right. Because that means that's exactly what I mean, right? Because for any point, you can try to find you can try to find a way to map this point to another point, any other point, right? So which is why what we say that the orbit, you only have one orbit, because this orbit can connect every point of your set. This group you can use a group element to map from one point to any other point, which is why the orbit is everything.
So the orbit is the only one orbit is the group itself. Not the
it's
group.
Not the group itself, it's a set itself.
Yeah, it's a set. It's a set itself, right?
Yes, that's right. Okay. Just imagine this group action is some way that it can help you to travel, right? And then the transitivity or transitively means, well, you do have the way to travel to anywhere. So which means the orbit or the way, the inventory you have, well, you have go to everywhere on the Earth. Then, well, the orbit of you is just everything, every place. Okay? Any other question? Okay, again, the definition here, these two definitions sounds very twisted, but again, this is just some word, okay? This is just some language so that we will not to repeat this kind of proposition of action or of a representation again and again in the future, okay? So, let me tell you why this kind of group action or group representation are so important for us. One of the reasons is it can help us to do something like the counting of elements. Let's say we have a group G act on the set S, okay? And let S in S. There is a one-to-one correspondence, which means there is a bijection F from the quotient group G over GS, or the G over GS to, this is actually not a quotient group. I'm sorry. This is not a quotient group. This is just a set of cosets. Okay, from this set to the orbit of S. From the coset of GS to the orbit of S. And this is a bijection. And again, let me mention this again. Since the orbit of S is just a subset of S, right? And this is just a coset or the coset of GS. So there is no group structure on any of them. which is why we can only say there is a bijection between them. Nothing more than that. Okay? In particular, well, the number of the orbit of an element is equals to the index of GS. If well, when they are finite, when they are infinite, this is actually also true, but we don't really write it as an equation. Okay. Let me see. Well, let's see why this is true. Why? Well, how you can connect with the coset and the orbit? What's the connection here? Well, the thing here is as we mentioned before, you can always try to use something like, well, you can always use a G. That is the idea. You can also, you always use an element in G to try to acting on the set S or an element on S. And when you're trying to use one element on G to act on S, then it may try to push this S, right? It may try to fix this S, doesn't change this S at all. If this G push S, then that means this G forms one additional element on the orbit. You push it so that you change this S. Then in your orbit, you have one more element. Otherwise, if it doesn't change, if GS equals to S, then, okay, the orbit doesn't change, right? This is our idea. So based on this idea, we can try to prove this proposition. So let me define this F for you. Let's define and coset GGS to be, well, acting on S, to be G times S. Okay, then you see it maps an element to an orbit, an element on the orbit of S. Then we have to say this F is first well-defined, right? And second is one-to-one, third is onto. Then we are done. Okay, so first, let's try to say this is a well-defined map, which means for different, well, representation or different representative element of this coset, of the element of coset, you should get the same output, okay? If GGS equals to G prime GS, we want to say the F of this element is equals to the F of this element. Then why is that? Is that clear for you? Well, it's actually not so hard, right? Since these two guys are the same, so yes, G can be written as G prime times something and something in GS. And this something can be seen as something like in the kernel of your operation, something like that, right? Then GS is equals to G prime HS with the proposition H acting on S doesn't change. It's actually fixed S. So it's well defined. Right? Remember, this GS is actually the stabilizer. So it doesn't change your S. So this is a well-definedness of this map. Then we have to show it's 1 to 1. Okay? Well, it's 1 to 1 because if f g gs equals to f, say, s, well, xgs. If there are two elements, they are the same. What does that mean? That means, well, xs equals to gs. Okay? You want to show that the cosets, these two cosets are the same. Then what does that mean? That means, okay, well, S is equals to X inverse G acting on S. You take the inverse of the operation X. So that means X inverse G is in GS, right? So that means, okay, G is in XGS. Similarly, X is in, well, GGS. So F, well, GGS equals to XGS. Same output means same input, so it's 1 to 1. Okay? Any question? And third,
Sorry, so why is GS a stabilizer? Like in the first part, when we prove it is well defined.
why what?
Why is GS the stabilizer? Like why HS just cancel? Like this H does not make any change.
You mean why this can cancel?
Yeah.
Because we say that these two are the same, right? Then that means G belongs to GS, right? GS is a subgroup. I mean, G belongs to GGS. So that means G belongs to G prime GS, right? Because GGS is equals to G prime GS. So that means G must equal to G prime times H, where H is an element on the stabilizer. Okay?
Yeah, I mean like why is GS a stabilizer?
That's a definition.
Well, we define this GS to be our stabilizer, right? So that we can do our work. Well, this GS is a name of stabilizer of S.
Okay, got it.
You cannot take any arbitrary subgroup and do this quotient and then say that there is a one-to-one bijection, right?
Yeah, got it. Thank you.
So it's 1 to 1. And it is also onto. Why it is onto? Well, it is onto for sure. This is actually a very easy thing to check. Well, it is onto because for any element, well, let's say T on the orbit, right? Then there exists some element, let's say G1 in G such that G1 times G equals to S. This is by the definition of the orbit. Right? I'm sorry. Let's say T equals to G1S. Then that means, okay, this F G1 GS is actually equals to T. So it's onto. Right? Onto is very obvious. So we prove that this GS is somehow like the kernel. And then you use G over this kernel, you somehow get the image, okay, of your group action. Any question before we move on? Any question? Any question? Okay. Then a natural corollary would be if G finite and acts on a set S, then for any S in S, we have the order of G is equals to the number of the orbit times the number of your the order of your stabilizer. Or at least the orbit of S for any S is a factor of the order of G. I think that's clear because this is what we learn for the Lagrange. One example is, well, we know that this T, the symmetric group of a equalatory triangle or S3 acts transitively on the set 1, 2, 3. Right? This is super clear. It's transitively. Then we know that for any S in S, what is the order of GS? What is a stabilizer as the number of stabilizer of this S? For instance, how many maps you know or you can find could be a stabilizer of 1? How many? What's the order? Anybody know? What is a stabilizer? What is what is the order of this stabilizer? Of course, this GS is a stabilizer of S, which means the element in, let's say, in this S3, such that G acting on S equals to S. For instance, what is a stabilizer of point 1? Well, the stabilizer of point 1 is all the G in S3 such that G maps point 1 to 1. What is the order of it? The question is. Think about it. What is the order of, for instance, G1? So if you want a map, which is a permutation on 1, 2, 3, to fix 1, what would be the option? What would be the only possible non-trivial permutation?
The reflection of diagonal of 1.
Yes, or you can just think, okay, since it fixed 1, right? Then it's either change or swap 2 and 3, which is G2 equals to 3 and G3 equals to 2. Or it keeps 2 and 3, which means G2 equals to 2, G3 equals to 3. So, which means you only have 2. In the sense, in the language of the triangle, that means you only have the reflection to be on the stabilizer. If you only have the reflection, then that means you only have this reflection or reflection square, which is identity. Right? Is that clear? So, which means the stabilizer of this group action always have order 2. Okay? How about the orbit? What is the orbit? Or what is the number of orbit?
3.
It must be 3. Why is that?
It is transitive.
It is transitive. That means you can use the element to maps from 1 to 2 or from 1 to 3 or from 1 to 1. You can always find this kind of map, right? So of course, for what kind of element on this set, you can always try to find from 1 to 1, from 1 to 2, from 1 to 3. You can go from here to here, here to here, or here to here. So the orbit or the road that you go is always 3. Okay, so well, you can recover the fact we already know that. So that means that 3 equals to 2 times 3 equals to 6 by this corollary. Okay.
Sorry, I still have a question for
Sure.
I think that according to the definition of transitivity, you didn't say anything about the only object here, not object, the only orbit there. So is it possible to have to let every element to have the same orbit, but not the whole set itself?
Well, you see, what is an orbit? An orbit is always a subset of S, right?
Yes.
So doesn't matter what kind of coset you have, doesn't matter whatever you have, right? Orbit only care about the element in S, nothing on the group, right? So which is why if you only have one orbit, it may be you may have some different things acting, may be very complicated, but when you're trying to see the orbit, it's super clear.
Yeah, I understand, but what I want to ask is, what is it possible to have orbit that is not the whole set itself, like the only orbit, not the whole set itself? Is it possible?
No, it's well, the only orbit, it cannot be the whole set, because when we define the action, right? When we define the action, that means this action can always is always well defined on any element, on your set, right? So which means if you use identity, it
Oh,
always give you back to this element, right? So
oh,
what means if you do want to find something, then this something, it must have some image.
yeah, you're correct.
Yeah, you cannot really only have one object, and this object is not the whole set. Because for the rest element on this set, it must have some image for some operation, for some, well, for some permutation on your group.
Yeah, sure. Thank you, Professor.
Mm-hmm. Any other question? Yeah, this part you have to try to imagine in your mind, which is somehow a little bit twisted, but well, it's not that hard. Try to imagine something is acting on something, and you try to push a point or push some element from here to here, from here to here. Okay? Any other question? Well, if no, let's have a 10 minutes break, and we will resume at 24. Okay? Let me pause this record. No? Okay, I start the record. So let's continue. Okay? We study the orbit and the stabilizer and the relation between the orbit and stabilizer, this kind of thing. And you may think that, you may find that this is something that really similar to something we learned before. And the reason why it sounds so familiar is because, well, this kind of change a set, you try to change a set or divide a set into the orbit, is actually given by, again, the equivalent class and equivalent relation, which is if two orbit has no intersection, well, has a non-trivial intersection, then OS is equals to OS prime. And S is equals to the unit of disjoint, well, orbit. Okay, which also means two elements in the same orbit, this define an equivalent relation between the element on S. This is actually the proof. A relation between a relation defined on this set S, say these two are equivalent if and only if they are in the same orbit, is actually an equivalent relation. Okay, why is that? Well, because first, then an element is actually in its orbit, right? S is equivalent to itself, and if S equivalent to S prime, then of course S prime is also equivalent to S, because you can S equals to G times S prime, then S prime is also equals to G inverse times S. S is equivalent to S prime equals to, well, equivalent to S double prime, then of course S is equivalent to S double prime. Okay, because it's just a two element on G, multiplication is also an element on G. Okay, so this gives us, well, basically what we did here is we use a group to define an equivalent relation so that we can divide this whole set of S into different equivalent classes. This is the idea about some application that we can use.
I think we learned the similar things in ODE, like the orbit.
Alright, yes. If you learn the orbit, then you have to learn this kind of thing. In the ODE class, I think the orbit is easier to understand, right? Because it's just something like the curve of the solution, so that you can see that, okay, you can travel from one point to another point, and everything is just on the orbit. It's really the orbit. Here, everything is discrete.
Yeah, and the orbit cannot like overlap because
Yeah, they cannot overlap. Otherwise, it will be a contradiction. And since we also know this, well, we know that S is equals to the disjoint unit of your OS. So that means the element of S is equals to the summation of, the number of OS disjoint orbit, right? So we have this relation about how to counting the total element of S. So from this equation, what we have is sometimes we can do some computation. This computation seems not so hard here, but later you'll see it's a very important idea that we can use. That is, for instance, if we know G has order 8, and maybe I shouldn't write this notation because that means the order of a group, but S is not a group. The number of elements of S is equals to, say, 15. Okay. Then the conclusion is this action, which is G acting on S, must have a fixed point. Why is that? A fixed point means, well, some element of G acting on a fixed point means any element on G acting on this S, this element in S, is it doesn't change. We call S is a fixed point. Why is that?
This is because all OS must be a divisor of 8. It should be either 8, 4, 2, 1. And the number of elements in S is 15. So there is something like there must be an odd number that is 1, at least
yes.
now. And 1 means the fixed point.
Yes, 1 means the orbit corresponding to this point has only 1 point, right? So which means whatever you use the element of this group to push this point, it doesn't change. It will not move, right? This is how you use this formula to show this result. Seems not very trivial, but it's actually easy to see in some sense. And let's see another application of the group action, okay? And this kind of counting theorem. Well, we have actually a proposition. The group, which I think I asked you to do, to try to do some analysis on this, on your homework, GL2 Z2. I hope everybody knows this group. Well, how does this group look like? But here I want to say that it's isomorphic to S3. Okay. Well, first GL2 Z2, it looks like it forms by matrices, right? And the matrices must only take the entries to be on Z2, which means it's either 0 or 1. And it's 2 by 2 matrices. And it's invertible, right? Which means the determinant is not 0. So which means you only have finite many options. And for instance, you have this identity matrix. You have this, not identity matrix, but we have with additional 1 here. Maybe this 1 could be here. And you cannot both to be 1 because it's not invertible, but you could have something like, like this, right? And you may have something like this. It's also not invertible. The determinant is actually to be 0, to be -1. And you also have this kind of thing. 1, 2, 3, 4, 5, 6. You have six elements. So, that can be make isometry to this S3. Otherwise, it cannot. It cannot be isomorphic to S3, right? So totally, you find that GL2Z2 has 6 elements. And here, I want you to prove that it's isomorphic to S3. Well, of course, based on the result we did last time, if a group has order 6, then it has only there are only two kinds of groups, either S3 or Z6. And you can see that this GL2Z2 is not Z6, so it must isomorphic to S3. But here, we can give another proof to prove that this group is isomorphic to this group. Let's see. Let's see how we can do this by using the group action. Here, let's say this group, let's call it G for simplicity, and let's call this Z2 to be, say V, say F, okay? And then we can call this V to be F squared. Well, you may try to think about this kind of space, which is like R2, so that you can use an element on this GL2Z2 to acting on this R2. That's a very nature action that you can imagine, right? So G acts on V. Okay, and you can see that V is actually equals to what? V actually equals to 0, 0, 1, 0, and 0, 1, and 1, 1. You only have 4 elements on V. Okay. So G can act on V, and you can see that G will fix 0, 0, right? Whatever you multiply by 0, 0, it's just a 0, 0, right? So which means instead of G acts on V, we can say that G acts on V subtract 0. Okay? And the thing here is, G acts on V subtract 0. It only have the number of this set is 3. So which means phi, there is a homomorphism from this G to the permutation group of 1, 2, 3, or S3. Sorry. Right? This is by the definition of group action. And here, what we can say is, this homomorphism is, first it's a homomorphism, and it is an injection, which means G is faithful. Why G is faithful? G is faithful. That means, well, for any G in G, if this element keep everything on V subtract 0 to be the same, then this little g must be the identity. Why is that? Why G will, for G not equals to I, for little g not equals to identity, G cannot maps 1 0 0 1 1 1 to be 1, well, it maps 1 0 to 1 0 0 1 to 1 0 1 1 1 to 1 1. Why it cannot? Any idea? For matrix here, if you use this matrix to acting on to multiply these two elements, E1, E2, E3, if this matrix maps E1 to E1, E2 to E2, E3 to E3, what we can conclude? So this is a matrix problem. What can we say? Why is that?
Independency.
What was that?
Wait, let me think about it.
Oh, it's easier than your thought. Okay, you see, you have these guys, right? G multiplied by 1 0. What do you have?
The first column of
the first column, right? This is the second column. Or you can combine these two guys, say that, okay, G times 1 0 0 1 equals to 1 0 0 1, right? So that means G equals to 1 0 0 1, right? So we have G, this capital G is faithful. Or I shouldn't say capital G is faithful. I should say this phi, this homomorphism or this representation is faithful, or phi is injection. Moreover, this G has 6 elements, S3 has 6 elements, so phi is isomorphism. Right? So we are done. You see, here we didn't check any rules of the operations on G. We just use this G to acting on some set. Then we get what we want. Okay? Any question? Well, another example to apply this group action or the idea of group action is, as we mentioned before, you can think the set S to be G itself, which means you use a group to acting on this group itself. So there is a homomorphism from G to the permutation group of G, which is you try to see G as a, well, as a set that contains n letters. N is the order of G. Okay, and you can map this G times X to be GX. GX both belongs to G. If you think it this way, then what we have is so-called Cayley theory. The Cayley theory, which is very interesting theorem. Every finite group G is isomorphic to a subgroup of a permutation group. If G has order n, then it is isomorphic to a subgroup of Sn. Okay? So which means whatever group you have, even though it seems that you have a lot of groups in the world, but as long as it's a finite group, it can always be seen as a subgroup of Sn. You can imagine how complicated of the subgroup of Sn, right? Why is that? Why is that? Well, the proof is very simple. You can notice that this representation, you use this group acting on itself is faithful. Which means if there is an element that doesn't change all the elements, if G times X is always equals to X, then of course this G is equals to identity, which is why this representation is faithful. Okay? So which means this homomorphism is always an injection. Okay? Any question? Any question? If no more question, then let's try to see another kind of operations that we have seen a lot of times last week, okay? Which is a conjugate. Before the conjugate, let me involve this kind of proposition so that you can get some warm up of our operation of conjugate. Let's say G act on a set S and S in S, okay? Suppose you have another element which equals to A acting on S. The question here is, then what's the relation between the orbit, well, not the orbit, the invariant, the stabilizer of S and the stabilizer of S prime? Well, the magic here is then, I'm sorry, this is S prime, this is S because S prime S. This as a subgroup is actually the conjugate of this subgroup. So you do a multiplication here on this element, then the stabilizer will do a conjugacy. Okay? Which is why I always, maybe I didn't say this a lot, but I probably should say this a lot. The conjugacy, the conjugate of element or the conjugate operation is very crucial in group theory. Okay, because it's trying to study the commutative of two elements. It can be seen as a replacement of a billion. Let me prove it. Let's say, well, you want to show these two guys are the same, right? Then that means you want to say this is a subset of this and this is a subset of this. Let's say if G is on the right-hand side or left-hand side, then A inverse GA acting on S. Let's see what happened. A inverse GA acting on S is equals to A acting on S. Is equals to A inverse G. A acting on S is S prime acting on S prime. All right? So it's A inverse acting on G S prime. G is a stabilizer. A inverse acting on S prime. A inverse acting on S prime, then it's S. S prime equals to AS. Right? So G, well, I mean, A inverse GA. A inverse GA is in GS prime. I'm sorry, it's in GS. Right? A inverse GA is in GS, so that means, okay, well, GS prime is a subset of A, you multiply A here, GS A inverse. Similarly, you can prove, I will not prove it here, G, well, you can also show that GS is a subset of A inverse G prime, GS prime A. So which means, okay, GS is A inverse is equals to GS prime. Okay? Any question? So you can imagine why this is true. It's just like you try to push this S to S prime. Then use your operation to acting on it. Then you try to push it back. Okay? You try to push this S prime back. Then eventually you get an S. Push forward and then push back so that you get some operations on, well, its own, right? On the original one. This is very important. This is our idea. Later you may see this kind of thing. Push forward, then push back. You may see this kind of map when you learn the geometry. You may learn when you learn the differential geometry or something like that. Okay? And give you an example. For instance, G is a group of isometry of plane. Of the plane R2. What is the meaning of isometry? It just means that, well, it maps R2 to R2. It's a map from R2 to R2. If you have learned geometry, the analytical geometry, or maybe in your linear algebra class, you may know that the isometry can only be formed by something like well, translation or rotation on R2. Okay? Or the reflection. Then let's say G0, because you can see it as a group action. G can be, well, the group of isometry can be seen as this group acting on R2, right? Then G0 is a stabilizer of 0, which is the isometry fixing the origin. And GP is an isometry fixing the point P. Okay? So, well, P is some arbitrary point on this RG. Then, what you know is, okay, let's assume this tau is a translation such that at any point it maps to x plus p, which also means tau, it maps 0, the origin, to point p. Then tau is an element in G. Okay? Then what we do know is GP is equals to tau G0 tau inverse, which means all the isometry that fix one point, that fix the origin, can be seen as a conjugate of isometry that fix the point P. By taking that, okay, by taking this, well, if you want to find an isometry that fix the point P, you just need to push this P to the origin and run an isometry on this, like a rotation or reflection along this origin, and then push it back to this point P. Okay, so this is an example from geometry. Any question? Well, this is something I believe something new for you. So, well, if you don't understand it, it's totally fine for this example. But I hope you can understand it because this is something very basic and it's something you understand. It's understandable for you after you learn the linear algebra. Okay. This is some basic about the analytical geometry. Question?
Can you explain isometry?
Yeah, the isometry just means a map, or you can think it's some kind of it's a map from R2 to R2, and it keeps the metric. It keeps the metric on R2. Okay, so which means if you know that 2 points has distance 1, then from this map, it maps this 2 point of distance 1 to another 2 points with distance 1. It doesn't change the length. Then we call this kind of map, this kind of, bijection on R2 to be isometry, which is something that keeps the metric on R2.
Okay, thank you.
But this is something maybe you don't really know. This is fine. But you can just imagine it's just some rotation, okay? Just some rotation.
Actually, we learned the similar things in ODE.
Oh, really? That's nice. Yeah. Then that means yes. But well, that's nice. Yeah. If you learn, yeah, that's right. You must learn something in ODE as well, because you need to have this kind of push forward and push back for some point. And yes, that's right. Great. And you can see that we have this kind of idea. This kind of idea, I believe, is originally from abstract algebra. Then you can use it to study this dynamical system. Yeah. Okay. So, since we mentioned this, conjugacy, the conjugation is very important. Let's discuss about it when we discuss the group action. This is conjugacy, which can be seen as another kind of group action, which is, well, you use this group, this element on this group, and this is X on your set. You map it to Gx G inverse. Of course, this doesn't make sense if your X is some set, some arbitrary set. So this kind of group action is, well, particularly to be used in study this kind of, well, group action on itself. When we try to study the group action of a group acting on itself, then this would be another way to another very usual way to define an action, right? Then, if you define this kind of thing to be a group action, what do you have is, okay, the stabilizer will be changed on, well, stabilizer on the previous group action, which is Gx equals to X, those kind of G, will be changed to be the centralizer of an element, which we denoted as Zx to be, well, G in G, such that Gx G inverse is equals to X. Okay, and which is all this G such that Gx equals to Xg. So-called the centralizer. I think we didn't mention this before, but it's just all this element that commutes with X. Okay? And you can see that this conjugacy action can also be, well, it's also can divide a group. Now it's a group into different classes because one element conjugate to another element is an equivalent relation. Okay, so which means, well, the conjugacy classes is still equivalent classes. Let's call this Cx again. This is the conjugacy classes, or the something like the orbit of an element X. Here we use Cx. X prime is in, to mean the conjugate class. X prime is in G such that X prime is equals to Gx G inverse for some G in G. Right? The conjugate classes, it can be seen as an orbit under this kind of operation, under this kind of action. Okay? You have stabilizer, which is centralizer in this situation. You have the conjugacy class, which is the same as the orbit in this situation. Okay? So we also have, since this is a conjugate class, since it is an equivalent class, so we also have G is equals to Cx times Zx. And Zx is a subgroup of G. And meanwhile, we have the same counting formula that we have before. This one. G as a set S can be written as the union, the disjoint union of different orbits. Here it can be written as the disjoint conjugate class right? Of your element. Or we can write it as well, if it is finite, if G is finite, we can somehow write it as C1 plus CK. But be careful here, this is a little bit well, confused about the notation. This C1 doesn't mean 1 is an element on G. This CK doesn't mean K is an element of G. We just use it as an index, okay? This doesn't mean that, well, this is a little bit confused, but we just make life easier. Don't write it somewhere else so that it will be really confused. I don't want to write it on the top, okay? So that it will be really confused otherwise. But here, this just means you have summation. You have the summation here. And this one, just like you try to do the partition of a set as a summation of orbits. This one is so-called the class equation of G. You try to divide G into different conjugacy classes, which is so-called the class equation. G, the order of G is equals to this kind of conjugate classes. The number of the conjugate classes, you take the sum. Okay? And you know that the numbers, well, it's even better than before. On the right-hand side, these numbers, well, on this orbit, these numbers, this number of orbits are only factor of the order of G. But here, these numbers are actually a factor of the left-hand side, right? Moreover, at least one of them equals to 1. Why is that? Do you know which conjugacy class has only one element? Which conjugacy class has only one element? Which one? Any idea?
The identity.
Yes. Why is that?
Because G identity equals to G, and G inverse is identity, and there's no other element that satisfies this kind of.
Yes, you cannot map E to something else, right? So which means, or the conjugate class only have E itself. It cannot have any other thing, okay? So that also means, okay, well, if you have an element that is on the center of the group, which means it commutes with any other element, then the conjugacy class of this element, the element on the center, has only one element, right? Let's see an example. Again, our favorite group, which is not so hard, not so easy, this T or S3, identity, the counterclockwise rotation, rotated twice, and well, it has reflection, and the reflection, well, R times F and R squared times F, with FR equals to R squared F. generated by these two elements, and this is a relation. Well, what if you have FR? Okay, and you can see that these are all the elements on this J. Now, let's try to find all the conjugacy classes and then find the class equation of this set. You may find it's not so easy. It's kind of tedious, but we can do that. Okay, let's try to do it. First, you know that the identity by itself forms a conjugate class. Okay, now let's see who are in the same conjugacy class of R. Okay, so then we need to use some element to do the conjugation of this R. Okay, for instance, with 1, well, this identity doesn't change this R. If you use R to do the conjugacy, you will go back to R. Of course, right? And what if you use R square acting on this R? Okay, R square acting on R minus 2, it still gave you R because R square and R, they commute with each other. That's also trivial. Now, something not so trivial happens. What if you use F to acting on this R? This is not so easy, right? But it's
R square.
hard. What's that?
R square.
It should be R square, right? Because FR equals to R square F. So FR is R square F. This F and F inverse, they cancel. So it's equals to R square. Okay, we find the orbit or the conjugacy class must at least contains R and R square. Okay. Then what else? We need to check this RF. RFR, RF inverse. What does it give us? Well, we need some computation, right? First, RF will give you R square F. So R square and R, they cancel because R cube is equals to identity. So RFR equals to F. F times RF inverse. RF inverse is F inverse R inverse. So F inverse cancel F inverse. F inverse cancel F. So it's R inverse. So it's R square. Okay. And similarly, if you use this guy, R square F acting on R times F square with R square F inverse, you still get R square. Okay, so we can conclude that the conjugate class or the orbit of R is R square. Okay. Then we know that, okay, the rest 3. Now the only problem is we need to check the rest 3, are they in the same conjugacy class or are they in different conjugacy classes? Any idea? Are they in the same or different conjugacy classes?
Yes, they are in the same.
Why?
That's like have like that's very much like the how to say the coset of the right coset of the 1 R square by F, something like that.
Well, that's true, but then how can you get connection between coset and this kind of conjugacy classes? That's not so easy.
Then maybe just use the theorem we introduced above over there.
What's the theorem?
because the number of the whole group is 6, and we have 2 conjugates classes. One the order is, I should not say the order, that like one has 1 element in it and one has 2 elements in it. So and the other, so the composition should be like 3 or 1 plus 2 or something like this. And but we cannot have another like we cannot wait at least one maybe
you could have 1 plus 1 plus 1. You could have 1 plus 2. You could have a 3, right? Now the question is it possible to have 1 plus 1 plus 1 or 1 plus 2? Well, actually, what's the meaning of a conjugacy class has order or has only 1 element? A conjugacy class has only 1 element is equivalent to say,
it's like a kernel.
Is equivalent to say what? It's like right? The conjugate class only have 1 element. That simply means it commutes with any other element of this group. It's in the center of this group, right? So if we want to see whether there is some 1 or not on the other conjugate classes, we only need to check whether it commutes with other element or not. If there is 1 element that is not commute with, then we can say that it's actually, well, not a 1. It's not on the center, right? This is the logic. So we can check F is not commute with R, right? RF is not commute with R as well. Of course, it will not. R square F is not commute with, well, with R or R square or whatever, F, for sure. So none of them commute with everything, every other thing on this group. So which means you don't have any other conjugate classes that has element only 1, has only 1 element. So which is why you must have a plus 3 here. Okay. Any question? This is how you can write the class equation of a group. It's not so easy, right? It's not so easy to do this kind of computation in general. Any question? So as long as we can do this kind of action and we have this kind of thing, well, there are a lot of very interesting applications of this conjugacy or conjugation, like a group action. Let me try to show something to you so that you will see why we are interested in this group action. You use group acting on itself, why it's interesting. Okay, and this is also somehow related to the CELO group that we are going to, well, introduce next time. So we say G is a P group if the order of G is equals to some power of P. Okay. So if the element of P is equals to P, the element of G is equals to P, then we know that G must be a cyclic group. It's ZP. But now let's think about what happens if you have a P group instead of this ZP. Okay, P prime. We always mean that P to be a prime number, so that it will be easier for us to argue, easier for us to do analysis. Okay. Then the first proposition we can get from what we learned today would be the center of a P group as order is always non-trivial. The center of a P group is always non-trivial. Okay, we know in ZP it's a billion, so the center is everything. But here, what we say that even if you have a P group instead of ZP, we still have the center of this group is non-trivial. Can you see why? Can anybody see why? This is why this proposition is kind of obvious.
Yes,
Yeah.
because if there is only one, like if the center has the order one, then so C is equal to the sum of every conjugate classes, and so which means the sum of every other classes is like P to the power of n minus one, and but we have that.
Well, it may not be P to the power n minus one, right? The conjugate classes could be anything, right? Could be anything that is a factor of your P to power n.
I mean the sum, sum, like
the sum of conjugate classes.
Yeah. The like so assume there the center has order one, then the net. Yeah, this is what I mean. So the sum of every other conjugate classes is P to the power of minus one, but we also know that. Yeah, but we also know that the latter part, every element of the latter part is divisible by P to the power of n.
That's right. Which means this is actually a multiple of P.
Yeah, so this is impossible.
So we are done. Right? So the proof is actually pretty easy, but it tells us something really interesting, right? That means in a P group, it must have something on its center. Then we will have a proposition, a corollary to this one. Let's say G is a P group, and S is a finite set on which G acts. Assume S, the element of S is not divisible by P. The conclusion is there is a fixed point. Right? This is exactly what we have done before. Exactly this one. So in general, as long as we know the idea of P groups, we know that yes, in general, this kind of argument is always valid. You can see this as a byproduct of the idea of this one. Or this can be seen as a byproduct of the idea of this one. Okay, and lastly, maybe, well, not lastly, we have still something I want to mention. Another corollary to this non-trivial center theorem about the P group. Every group of order P squared is abelian. Well, if you know this, then you don't really need to say anything about this your homework problem, right? There's a homework problem say that any group of order 4 is abelian, right? Why is that? Why is this is true? The question is. Let's try to do some computation, okay? Let's say we want to show that for any x, the center or the the centralizer of this x equals to g. Then that means, okay, that means this x is in the center of G. Let's say if x is not in this center of G. Suppose you have this one. Suppose you have some kind of x, some element that is not on the center, so that it makes this group non-abelian. Okay? Then we know that Zx contains everything on the center, right? Anything on the center must be on Zx, because anything on the center, it commutes with x. It commutes with any other element. But meanwhile, x is also commute with x, right? So which means the order of this set is at least as bigger than this center of G. Okay? Okay, so what does that mean? You have the center. This is the center of a P group, right? This guy is non-trivial. So either this guy equals to P or is equals to P squared. It cannot equals to 1. It's a subgroup of G. So it cannot be 1. It must be P or P squared. So that means, well, and we also have the number of Zx is a factor of G. So that means it must equals to P squared, or Zx equals to G, which is a contradiction. Okay, so any x in G, x is in CG. So any element of order, well, every group of order P squared, no matter what P, is abelian. Any question? And from this, a direct corollary is every group of order P squared is either ZP square, a cyclic group, or its isometry to ZP cross ZP, which means all the group of order P square have the simplest structure we can imagine. Okay. Why is that? Well, if there exists G such that it has order P square, then G is isometry to, well, isomorphic to ZP square. Well done. Otherwise, every element G in G, G is not equals to identity has order P, right? Because the order of the element must be a divisor of the order of G. So that means, okay, let's choose, well, let's choose, say A in G, A is not equals to identity. And we have one cyclic group well generated by A. Okay. Now we can choose another different element B, which is not in this generated group. Then we know that we have two things, A and B. An interesting fact is, since G is abelian, because G is of order P square, we know that P square is an abelian group. So that means, well, these two finite generated group are all normal. Right? We also know that the intersection of these two guys, of these two normal subgroup, must be identity, because we choose B not belongs to this A. So of course, they don't have any joint element. Okay? So, well, what do we have? Well, I mean, I'm sorry, this is not so clear. Maybe I should write it more clear. The element of this set is actually less than the element of this cyclic group, which equals to P. Because B is not in this set, B is not in this set, so that means the intersection of these two guys must be has order strictly less than this generated group, but the group generated by A. So that means because this is also a subgroup, so that means it only have one element, so B intersect with A is only identity. Now we have two subgroups. Normal subgroup. Intersection equals to identity. So that means, okay, B times A is isometry, is isomorphic to B cross A. Now the last step is we only need to show this is actually equals to G. Why is that? Again, we can try to compute the number of elements of this set. We know that the number of elements of A is P. The number of elements of this group, it contains all the elements of this group. It contains B, which is not in this group. So it's at least P. So which means it's well, and also since both of them are normal subgroup, so it's a subgroup or maybe I should say the order equals to p squared. That means BA equals to G. So as a conclusion, G is isomorphic to B cross A, which is ZP cross. Okay. Sorry for the delay, and that's all I want to mention about the group action today. And from now to 3:30 is my office hour, and I will end the recording. In case you have any question, do you have any question before we end the recording? Any question? If no,
a lot of questions, but I'll need to read first and then maybe ask questions.
okay, that's fine. So that's ended, and now it formally becomes my office